Welcome to day 28 of our low-level design course. Today, we will be diving into a real-world system design, the low-level design of a cab booking system similar to platforms like Uber. This system is critical in today's on-demand economy, and designing such systems involves both understanding the business requirements and how to translate those into a robust, scalable software solution. In this session, we will explore the design of the core components, their interactions, and how to handle scalability, concurrency, and real-time operations. Let's take a look at the agenda for today's session. First, we will start by introducing the concept of a cab booking system, understanding how such systems operate and the key features they provide. Then we will work on gathering the core functional and non-functional requirements for our design. After that, we will identify the primary entities in the system and explore how they interact with each other. We will spend some time on designing class diagrams, defining their responsibilities, and identifying key operations that the system will handle. Towards the end, we will discuss advanced concepts like real-time updates, concurrency, and pricing algorithms, and conclude with a homework task that will help you expand the design further. To begin, let's understand what a cab booking system is and how it works. A cab booking system connects riders with drivers in real time. Think of platforms like Uber, Lyft, or Ola. When a rider requests a cab, the system uses their location and the availability of nearby drivers to match them efficiently. A smooth experience depends on how quickly and accurately the system can process this request. The system must also handle features like ride tracking, fare calculations, and payment processing. Today, we will be focusing on designing a system with a real-time communication and scalability to ensure that it can handle thousands, if not millions, of simultaneous users. Before we dive into the actual design, we must gather the core requirements for the system. The functional requirements for the system include rider requests a ride. The rider should be able to enter their destination and request a ride. Driver accepts a ride. Drivers should be able to accept or reject ride requests based on their availability and proximity to the rider. Real-time ride tracking. Both the rider and the driver need to see the progress of the ride in real time from the pickup location to the destination. Payment processing. Once the ride is completed, the system should calculate the fare and allow for payment. Non-functional requirements involve performance, scalability, and reliability. The system must handle millions of users concurrently, process real-time data with minimal latency, and be fault-tolerant. We will also need to make the system extensible to support additional features in the future, like ride pooling or multi-city operations. Now that we have our requirements, let's identify the key entities that make up our cab booking system. The primary entities are rider. This entity represents the user who requests a ride. It holds information like the rider's name, current location, and destination. Driver, the entity representing the person providing the ride. It stores details like the driver's name, availability, location, and vehicle type. Cab, this represents the vehicle being used by the driver. It has attributes like cab type and it is associated with the driver. Ride, the central entity that connects the rider with the driver. It contains the ride details such as start time, end time, and fare calculation. Location, this is a crucial component for calculating distances, matching riders to nearby drivers, and updating real-time positions. Understanding the relationships between these entities will help us design a system where interactions are smooth and efficient. Let's explore the design of our classes in more detail. First, we have the rider class. It contains attributes like rider ID, name, current location, and destination. The main function of this class is to request a ride, which involves providing a destination. Next, the driver class stores driver details like driver ID, name, current location, and availability status. It also has methods for accepting or rejecting rides, which is essential for our system's workflow. The cab class is associated with the driver and holds information about the type of cab, such as whether it's a sedan or SUV. The ride class ties everything together. It manages the relationship between the rider and the driver, including start and end times, fare calculations, and ride statuses. Each class has well-defined responsibilities, and the interactions between them are essential for a functioning system. Here's a glimpse of how we can implement one of the key operations in this system, ride matching. This involves finding the nearest driver to the rider's current location. We do this by looping through all available drivers and calculating the distance between the rider and each driver using their location data. The driver who is the closest to the rider is selected to accept the ride. Here's a code sketch of how this operation could look. The find nearest driver function calculates the distance for all available drivers, compares them, and returns the closest one. This operation is key to ensuring that riders get matched quickly and drivers don't waste time on long distances. As we move forward, let's dive into some advanced concepts that will help us optimize and scale the system. Real-time updates. For ride tracking and notifications, we need to ensure that updates happen in real time. This can be achieved using technologies like WebSockets or long pooling, which keep the client updated without constant refreshing. Geo-indexing. To efficiently find nearby drivers, we can use geo-indexing methods like quad trees or KD trees that allow fast searching based on geographic location. Concurrency. Given that the system may handle thousands of riders and drivers simultaneously, concurrency management is crucial. We need to ensure that operations like ride matching or status updates are thread safe. Surge pricing. During peak times, prices should dynamically increase to balance supply and demand. This can be implemented using a surge pricing algorithm that adjusts fares based on real-time demand data. To wrap up today, we have designed the core components of a cab booking system, focusing on entities like rider, driver, cab, ride, and location. We have worked on class diagrams, defined responsibilities, and explored some key operations like ride matching. For your homework, I would like you to extend the design by adding features like ride cancellation. How do you handle cancellations and penalties for both the rider and the driver? You can also consider implementing a rating system for both riders and drivers. Think about how to ensure that future enhancements such as multi-cab options or pool rides can be easily integrated into the system. Lastly, here's a simple UML class diagram that summarizes what we have discussed today. The rider requests a ride which is accepted by a driver. The cab is linked to the driver and location is used for distance calculations between the rider and the driver. This diagram helps visualize the system architecture and gives us a blueprint to build our system further. I encourage you to refer to this diagram as you extend your designs and implement additional features. And thank you for your attention.